Hello everyone, so today we're going to talk about n by n matrices. We defined the norm of A to be the sum of the absolute value of arrays of A. As you will see, there is nothing particular about this norm. All we need is some way of saying that all arrays of A are small and near zero. So what we need to prove is that there exists some epsilon positive such that for every A n by n matrix, the norm of A less than epsilon implies that there exists some n by n matrix B such that A equals B squared plus B. In other words, this equation A equal B squared plus B has a solution if A has arrays that are quite small and near zero. So for the solution of this, we're gonna surprisingly apply the inverse function theorem. So define f from the space of n by n matrices to itself via B maps by f to B squared plus B. So that's a well-defined map. If you have n by n matrix, then B squared plus B is also an n by n matrix. So we identify this space of n by n matrices by r to power n squared. So it can be regarded as just a Euclidean space. But we don't want to actually make this identification, and we want to keep working with matrices. In particular, because we want to talk about derivative of f. So to compute derivative of f at a point B, we need to find directional derivatives. Directional derivatives. And to find the directional derivative in a particular direction, what we do is try to understand how adding epsilon v changes the values of f. So v is another n by n matrix, and epsilon is a real value. So we're talking about adding epsilon v to the fixed point B, and we want to compare it to the values of f at B. So epsilon, you can think about it as being small. So by definition, so this will be B plus epsilon v multiplied with itself. Because we don't have non-commutative matrix multiplications, we don't want to write power 2. It won't help with calculations, so epsilon v. And this will be B squared. Then there is B that I want to bring back here. There will be epsilon v times B plus B times V. And then there will be epsilon v again, and there will be epsilon squared v to power 2. And this you can see that is equal to f of b plus epsilon vb plus bv plus v plus epsilon squared v squared. So this part here, you can see that this is the order 1, in other words, linear part of this expression, the other part has epsilon squared, which is negligible if epsilon goes to 0. Or you could just subtract fb from both sides and divide by epsilon and let epsilon go to 0 to get the directional derivative. So as a result, directional derivative of f, that is derivative of f at b, applied to v is equal to v times b plus b times v plus v. In particular, so this describes the Frechet derivative of f at b. So it's one of those funny cases where you don't have the derivative per se, but you know what the derivative does once you apply it to any direction. So we are interested at b equals 0. So in particular, derivative of f at 0 applied to any v is just v. So it's kind of the identity operator. So derivative of f0 is invertible. Therefore, by inverse function theorem, which applies because the map f in each array is a polynomial in terms of arrays of b. So it is a C infinity function, in fact. And now that the derivative is non-degenerate at 0, the inverse function theorem claims that there exists an open neighborhood of 0 on which f is a diffeomorphism. So to see in pictures, so here is your space there, so here is 0, and notice that 0 maps to 0 with f. And the inverse function theorem claims that there is some open neighborhood of 0 and an open neighborhood of 0 back there, so that f diffeomorphically maps these to one another, and f inverse, of course, too. Therefore, so if you call this u, and this is v equal f of u, then for every a, so every a in v, there exists some b from u such that a equals f of b, but f of b is just b squared plus b. And that is the end of the story. A very surprising application of inverse function theorem and to a kind of maybe linear algebra problem that every matrix A, provided it has small arrays, can be written as b squared plus b for some b. Because you have b squared here and just b here, there is no scaling argument to extend it to all matrices A. Because if you start with any matrix A, you can multiply by a real number with tiny real numbers so that every array becomes small, and then you can apply what we have proven already. But then you cannot scale B the right way so that it works for this large A as well. So we have to contend with this local result and leave you with the exercise that is the result true. So is every a n by n equal to b squared plus b for some b? And if not, what is the abstraction? Honestly, I don't have the answer at this moment, so if you know it or if you have some ideas, put them in the comment, and see you in a near future video. If you have not yet subscribed, please do so, because that's the best way you can support my channel. Thank you for your attention.